Hello students, this is Professor Chalai, and in this video I'm going to go over some of the things that you need to know for your magnesium and hydrochloric acid reaction pivot lab online. So let's get into it. In this lab we're going to react a metal with an acid. Now the metal that we're going to react is magnesium and the acid is going to be hydrochloric acid, but for this sort of the practice calculations that I'm going to do in this video, I'm going to change that. I'm going to change it from magnesium to sodium. And I'm going to change hydrochloric acid to sulfuric acid, just so that I can give you examples of these and I'm not actually solving the problems for you in this video. So we're going to look at the reaction between sodium metal and sulfuric acid. So sodium metal here means that we're dealing with a solid, not an aqueous solution. It's a metal, it's solid. So in writing the balanced chemical equation, we'll have sodium solid. It's reacting with sulfuric acid, which the formula for that we know is H2SO4 aqueous. Now, we know that sodium tends to form positive charges, but in sodium solid, there is no charge because, you touch a piece of metal, you don't get shocked. It means that it's charge neutral. It's elemental sodium, no charge. But sodium can form positive charges, as we know, in salts and aqueous solutions. And to do that, it must lose an electron. So I'm just going to write an electron there just to balance the charges. A plus and a minus charge gives us the neutral charge. So sodium can become positively charged if it gives up an electron. All right, what else do we know? We know that in H2SO4, we have two hydrogens or two protons, and SO4 sulfate ion is SO4 2 minus. So in this sort of reaction, sodium can form a positive ion and it could pair up with the sulfate ion. So sodium with a positive charge can pair up with the sulfate ion to form sodium sulfate, right? Aqueous. We just need two of the sodiums to pair up with one of the sulfate ions to balance the charge. So we'll need two sodiums to form two sodium plus, which will give us two electrons. So in this equation, we have sodium there, so let's put two sodium over there just to balance it out. Okay, but so what happens with these two electrons? Well, these two electrons pair up with these two H pluses to form H2 gas. And this pretty much happens with all metals when they react with an acid. They will form a salt and hydrogen gas will be released from that reaction. So keep that in mind when you're writing the equation for magnesium metal and hydrochloric acid. Okay, in this video, you'll see this reaction being performed, and as the gas is being produced, the volume in a test tube, the volume of gas in that test tube will expand or increase because you have more and more gas produced. And so in that video, they will measure an amount of magnesium. So we're working with sodium in this lab. So let's say you measure 0.123 grams of sodium. All right. So if you have 0.123 grams of sodium, they don't tell you how much acid you have. So we can assume that we have excess acid, right? The question is, what volume of gas is produced? And that's the question asked in number 3. They want you to predict the volume of the hydrogen gas. So how do we go about figuring that out? Well, to do that, I need to introduce the concept of molar volume. There we go. We haven't touched on gases yet, but what we'll learn, and some of you might have seen this equation before, is the ideal gas law equation is PV is equal to nRT. Some of you might have heard of this equation before. If we divide both sides by n, right, such that the n cancels out over there, divide both sides by p, such that the p cancels out there, we will get something like V divided by N is equal to N times R times T. V is the volume of the gas, usually measured in liters. N is the number of moles of gas. Sorry. We will get V over N is equal to R times T divided by P. There we go. N is the number of moles. R is something we call the ideal gas constant. And since it's a constant, the value is always 0.08206 liters times moles divided by, liters times atmospheres divided by moles times Kelvin. Temperature should be in Kelvin. So this is the temperature in Kelvin, and this is the pressure in atmospheres. Again, we'll go over all of these in more details. What I'm just trying to get to is the molar volume, which is this quantity right here. It's the volume of gas for 1 mole of gas. And to get that volume for 1 mole of gas, it doesn't matter what the type of gas is. All that it depends on is what temperature you're using and what pressure you're using. And to make this matter simple, we're just going to assume a temperature of 0 degrees Celsius or 273.15 Kelvin, right? Because we need it in Kelvin. And for pressure, we're just going to assume 1 atmosphere, which is the pressure of the atmosphere that most experiments are carried out in. So the molar volume then becomes 0.08206 liters times atmospheres divided by moles times Kelvin. That's the R value. The temperature is 273.15 kelvins. So Kelvin here will cancel out. And then the pressure will be 1 atmosphere such that the atmosphere cancels out. And we get a number like 22.4 liters divided by number of moles. So the volume divided by number of moles is 22.4 liters divided by moles as the units. This is all at 0 degrees Celsius and 1 atmosphere. Some people will call that standard temperature and pressure. Now, up to this point, this is, you don't need to necessarily do all of this calculations for your online lab. I just want you to know where we get this number from, the molar volume of a gas. So we know that any gas, if you have 1 mole of gas, it will have a volume of 22.4 liters as long as we're at standard temperature and pressure. So what we need to know then is how many moles of gas do we have? If we want to figure out the volume of gas, we need to figure out how many moles of gas do we have. Let's come back to this equation. We need to figure out how many moles of this gas that we have. Well, we have the mass of sodium and excess acid, so we're going to assume that this is the limiting reagent. If we know the mass of sodium, we can calculate the moles of sodium, and from the balanced chemical equation, we can figure out the moles of gas. So let's do that. So the moles of H2 gas will be, first we need to figure out the moles of sodium. We have a mass of 0.123 grams of sodium. To convert to number of moles of sodium, we need the molar mass of sodium, right? And that is 22.99 grams of sodium per moles of sodium. So grams of sodium will cancel out. Now that we have moles of sodium, we can convert to moles of hydrogen using mole ratios, right? For every 2 moles of sodium, there's going to be 1 mole of hydrogen. So let's include that. So for every 2 moles of sodium, there's 1 mole of hydrogen. So moles of sodium cancel out, and so for our answer, we plug this into our calculator. We should get 0.00268 to 3 sig figs moles of hydrogen gas. Okay, now that we know the number of moles of hydrogen gas, we can use the molar volume here to figure out the number of moles. But the question is asking us for how many milliliters of gas that we need. right? Because the experiment is measures the volume in gas in milliliters. So let's figure that out. So the volume of H2 gas, we know the number of moles, 0. Let's use a different color. The volume is right, the number of moles is right here, 0.00268. My pen is going wonky. Moles of H2, right? We know that the molar volume is 22.4 liters per mole. So if we multiply by that, 22.4 liters per mole, moles cancel out, and that will give us the volume in liters. But the experiment measures the volume in milliliters. So we know that every 1 liter is 1,000 milliliters. So that will give us a volume, if I did my math correct, of 60.0 milliliters. And so this will be our theoretical volume, right? It's similar to theoretical yield, except for gases, we're going to be measuring the volume of the gas, not the mass of the gas. All right, so let's go over that again. We needed the molar volume, which is in liters per mole. You can convert it to milliliters per mole if you wanted to. We needed to find the moles of hydrogen gas given the amount of metal that we started with. So we found the moles of sodium and the moles of hydrogen. And then we used that number of moles with the molar volume to figure out the volume of gas. This is very similar to other sort of theoretical yield calculations, to other stoichiometry problems. The only difference is we're dealing with gas, not a solid. So we need to measure the yield differently. All right. So I hope that answers a lot of your questions about how do we figure out the volume of gas. The other questions in this online lab should all be easier to follow. If you have questions, please reach out to your instructor. Otherwise, have fun with the lab. See you later. Bye.